Hessian, and this video is to walk you through Activity 4 in High Adventure Science, Sources, Sinks, and Feedbacks. Okay, so we're going to go ahead and get started. I'm going to click on the first page. Let me zoom in a little bit so you can pay a little bit better attention to what we're taking a look at. The first section is on the carbon cycle. Okay, carbon cycling in the Earth system. And what this talks about is that carbon dioxide, this is the greenhouse gas that is emitted by burning fossil fuels and during respiration. It says it's constantly being added to the atmosphere through both geological and biological processes. As rocks are weathered, carbon dioxide is released. Living organisms release carbon dioxide through respiration, and when they die, they release carbon dioxide as they decompose. Extra carbon dioxide is released when materials are burned, and these are all sources of carbon dioxide. So the question is, with all the carbon dioxide being added, why isn't the level much higher? And that's because there's a cycle. There's what's called the carbon cycle. Much like when we learned about the water cycle, there's a carbon cycle. So let's take a look at the flow chart. Okay, let's take a look at the labeled rectangles first. We have the atmosphere, the ocean, sediments, and land. And what this is showing is how carbon dioxide can move between these areas. So from land, it can move into the atmosphere. From the atmosphere, it can move into the ocean. And from the ocean, it can move back into sediments, which is part of the land. And it can go the other direction as well. So question one is, which statement is true about the carbon dioxide cycle? Reservoirs add more carbon dioxide to the environment than they remove. Carbon dioxide travels through the environment in a single direction. Carbon dioxide is constantly moving throughout the environment, and when carbon dioxide enters a reservoir, it no longer cycles. Of those, hopefully you notice that the best answer here is the third one. Carbon dioxide is constantly moving throughout the environment. Then question two, is there a reservoir that serves only to take in carbon dioxide? Explain your reasoning. So reservoirs are these. Land is a reservoir. Atmosphere is a reservoir. Ocean and sediments. A reservoir is a place where stuff is contained. So the question is there a place where carbon dioxide is contained where it never leaves? And by looking at this, you should look to see if there's any outflow arrows. And you should notice that every one of these four reservoirs have an arrow moving out of it. So the answer should be that no, there is no reservoir that serves only to take in carbon dioxide. The next page is solubility in the ocean. All right. The ocean has many substances dissolved in it, including salt. If you try to dissolve salt in a glass of water, you'll find that the more salt dissolves in the water when the water is warmer. So solubility of salt in water, how easy it is to dissolve salt in water is affected by temperature. Well, the solubility of gases is also affected by temperature. How does solubility of gas change with temperature? This is a picture that shows a model. It's not a working model. And it will show you the interaction between Earth's land, ocean, and temperature. So let's zoom in on this graph. This shows the air temperature change and the ocean temperature change. So the red line, the air temperature drops, and there's a little bit of a delay in the ocean cooling off or heating up. That's because it takes energy, it takes time to warm up and cool off water, more so than air. The next graph showing carbon dioxide concentration in green, as well as the amount of carbon dioxide in the ocean. This is being related also to the air temperature. So the top graph, the green graph showing carbon dioxide, notice what happens when the ocean temperature increases. Okay, notice what happens to the amount of carbon dioxide in the atmosphere increases, but look what happens to it in the ocean. As the ocean temperature increases, the amount of carbon dioxide in the ocean decreases. So that means as our planet warms, the ocean will hold less carbon dioxide, and so that carbon dioxide will move into the air. Okay. I'm going to go ahead and click out of this. Questions. Use the picture of the model to make a prediction about the effect that temperature will have on the ability of carbon dioxide to dissolve in the ocean. Will higher temperatures increase or decrease carbon dioxide solubility? That question is asking, as you warm up the water, will it be easier or harder for carbon dioxide to dissolve in the water? So, as you heat up the water, so that's the blue line in the top graph, what happens to the blue line in the bottom graph? It goes down. So that means it's harder to dissolve carbon dioxide in the water as the water heats up. Next page, it says using the temperature slider below the model to increase and decrease the temperature of the ocean. Actually, you'll be changing the temperature of the planet with the slider, but the ocean temperature will change with the planet temperature. The temperature of the ocean is shown with a blue line. Notice that the ocean temperature lags behind, all right? I talked about that a little bit before. So I'm going to go ahead and press this, and we're going to increase the temperature. That's the slider here. And you can see the temperature, air temperature went up in the top graph. And the ocean temperature lags behind. And then in the bottom graph, you can see that the amount of CO2 in the atmosphere then increases. And the blue line showing the amount of carbon dioxide in the ocean is way at the bottom. So let's cool everything down. I'm going to drop it all the way down. Now we are showing in a cooler planet what happens. Okay, as I cool the planet, you can see the blue line shows the temperature of the oceans decreasing, and corresponding with that, the blue line in the bottom graph is increasing. That's the amount of carbon dioxide in the ocean. So from this computer model, you should see that the relationship between the temperature of the oceans and the amount of carbon dioxide that can be held in the ocean, we call it sequestered or dissolved in the ocean, that is an inverse relationship. As the temperature of the ocean increases, the amount of CO2 dissolved in it decreases. And as the temperature of the ocean decreases, the amount of dissolved CO2 increases. So if you want to be able to dissolve a lot of carbon dioxide in the ocean water, cool it off. So which graph shows the temperature of the ocean? Okay, temperature of the ocean is the top graph, right? Which color line represents the amount of carbon dioxide in the atmosphere? You can use just this key for that. The green line does that. How does water temperature affect the amount of carbon dioxide that can dissolve in the ocean? Again, as the temperature of the water increased, the amount of water that could dissolve in it decreased. That's an inverse relationship. And which statement best describes the relationship between the temperature and solubility of carbon dioxide? When the ocean temperature is higher, less carbon dioxide can be dissolved in the ocean. I believe that's the correct one. And that is, the higher the water temperature, the fewer gases that can dissolve in it. Okay, we're going to go ahead and move on to the next one. We're going to skip this part. We'll go on to page 4. Page 4 talks about water vapor. Water vapor is a very powerful greenhouse gas. So it says in the previous models, you saw that carbon dioxide traps infrared radiation in Earth's atmosphere, and temperature increases with increasing carbon dioxide concentration. The actual temperature increase on Earth is greater than what we would expect if only carbon dioxide levels were taken into account. So what's missing? It says in the last model, you learned that oceans play a role as a reservoir for carbon dioxide. So the oceans can hold carbon dioxide, but oceans play more than one role. In this model, you'll explore the relationship between temperature and water vapor levels. So it says experiment with the temperature slider below the model. So I'm going to go ahead and press play. And let's decrease the temperature to begin with. So that's the top graph. The top graph shows air temperature decrease immediately, and then ocean temperature lags behind. And then the bottom graph shows the carbon dioxide in the atmosphere, the carbon dioxide in the ocean, and we're looking at the black line, the amount of water vapor in the atmosphere. Okay, as we let this play, now I'm going to increase the temperature, and I'm going to have you pay attention to certainly the red line first that shows the temperature going up, but look what happened to the black line. So we would call this a direct relationship. As you increase the temperature of the air, it can hold more water vapor so that it will increase the amount of water vapor in the atmosphere. So the questions, what color line represents the water vapor in the atmosphere? Water vapor in the atmosphere is the black line. How is infrared radiation represented in the model? That goes back to this screen. Infrared, remember, is the purple arrows. How does infrared radiation react with greenhouse gas? We saw that before. It's absorbed by greenhouse gases and re-emitted. I'll go ahead and click on the correct answers here. How is infrared radiation? By the purple arrows. We can check our answer, and check our answer. What's the relationship between water vapor and temperature? This is a direct relationship. We're referring to air temperature, and as air temperature increases, the amount of water vapor in the atmosphere also increases. Water vapor is a greenhouse gas. What do you think will happen to the temperature when the amount of water vapor increases? So if you know that it's a greenhouse gas, you should understand that as the amount of water vapor increases, it will hold on to more heat and the temperature will increase. And then you can go through the explain the answer. We're not going to do that. We'll go to page 5. Now, combining the effects of carbon dioxide and water vapor is the next one. Sorry about that. There we go. It says in previous models, you used a temperature slider to set the temperature. While this helped you figure out the relationship between temperature, carbon dioxide uptake by the ocean, and the amount of water vapor in the atmosphere, it's not very realistic. This model shows all of the relationships interacting with each other. All right. Just as in real life, the only factor you can control is the amount of carbon dioxide emissions. We're going to use human emissions for that in this slider. So if we take a look, I'm going to go ahead and press play. And let's take a look at our graphs. Top graph shows air temperature, right? These are percent of 2010 levels. So whatever the level of human emissions was in 2010 is represented here. And you can see that we have a warming atmosphere. It's predicting all the way into 2025, 2030, and so on. Down in the bottom graph, you can see the amount of carbon dioxide increasing. You can see the amount of water vapor increasing, as well as the amount of carbon dioxide in the ocean and water vapor. So, question, what does the human emission slider do? So this is controlling if you could magically increase or decrease the human emissions. Let me decrease it down to below 50%. And then you can see what effect that has. So the human emission slider controls the emission of carbon dioxide, is what I would say. That's the only thing we can control. Question 22, how does the level of carbon dioxide affect the level of water vapor? Well, when you increase carbon dioxide, you also increase the amount of water vapor, and that's because you're increasing the temperature, right? How do you know this? Take a look to see how the green line and black line track each other, right? As the green line goes up, so does the black line, and so on. So an increase is an increase in water vapor. What happens to the temperature when the atmospheric carbon dioxide increases? So we can certainly bump that up again if you don't know. Most of you probably know if we increase the amount of carbon dioxide, we're probably going to see an increase in temperature. We'll give it a little time to work. And you should be able to see that the temperature is starting to rise. And then you can go through and explain how you got that answer and so on. And we'll go to the last page. The last page talks about feedbacks. Now, we've mentioned this in class before. This is entitled multiple factors. What you saw in the last model is called a positive feedback. When there's a change in a system, the change gets amplified by further changes. One example of a positive feedback is studying to get good grades in school. When you study hard, you get better grades. Or you could say attendance in class, right? The more time you spend in class, the better your grade tends to be. So we call that a positive feedback. A positive feedback is when an input causes an output to increase, which then causes the input to increase. Okay. We're going to see that more in our next activity. So describe a positive feedback system that affects Earth's temperature. A couple of ideas here would be, one positive feedback would be, let's say, warming atmosphere causes more Arctic ice to melt. So you remember, ice reflects more sunlight. So that means there'll be more ocean. Opening up more ocean to absorb heat, causing a warmer atmosphere, which causes even more ice to melt. Now you can see how this would just keep going, right? A positive feedback loop. As ice melts, the Earth warms more, causing more ice to melt, causing the Earth to warm more, and so on. Okay, so far the models have only shown increasing temperatures, but obviously since Earth has had ice ages in the past, temperatures don't only increase. What kinds of things would decrease Earth's temperature? And that just has you kind of guess on that. Okay, that's it for today's lesson. Go ahead and finish this assignment and we'll move on from here.